My name is Patrick Kawamura. This is my final project presentation for CSCI E-88C. So the main goal of this project was to take state collision data and try to use it to identify street locations that needed to be investigated for possible improvements to help reduce collisions. The way this would be done would be to compute high collision streets and high fatality streets. A secondary goal would be to provide the states with various forms of statistical data, ranging from fatality, collision, and injuries per month, year, and city, collision event types, manner of collision, weather conditions, lighting conditions, road surface conditions, and contributing factors. The diagram for this starts with a local police agency, either their database or device, feeding the raw data into a data warehouse. For this example, I'm using the state of Connecticut. This raw data is then ingested and cleaned in the batch layer, as well as appropriate aggregations. The results are then output to the command window, and visualization was chosen to be done by Excel. The application. So we start with the collision case class. So the data I chose to use from Connecticut starts out with about 108 columns. So I needed to reduce it to the columns I would actually utilize and rename them to meaningful names. I do have an apply method that helps me clean the data as it gets input. I used a lot of helper methods to try to reduce the clutter of the code. Most of them were pretty basic, normalizing for a string or an int, checking if it's null and putting none or zero appropriately, checking if there's an invalid entry, putting unknown. The more challenging one was normalizing the street name. The street name field that they use is a text field, so largely they can put anything they want in there. So I needed to remove the numerics before streets, as well as the directions north, south, east, or west. And if they had anything following a normal street name ending, that also had to be removed. So that's what a large amount of this portion of the code does. So it checks if it starts with a letter, checks if it starts with a number, checks if it starts with a direction, and then we have helper functions to remove direction in the many formats it can be in, as well as to remove any invalid ending. So anything after your normal road, street, avenue, way would be chopped off to help stabilize the inputs. The program itself, we start with the main method, set up the configurations, take the input argument, which is the file, to be read. The first thing to do is to clean the raw data, which sends it through to get transformed into a collision object and cleans it. We then save that data, and then we change the name of the data so that it's more predictable. After that, we move into the transformation and computation. That new clean data is then loaded into a collision data set, and then we have about 16 various aggregations that are performed throughout the rest of the main. After each one of those aggregations, we do have a print statement to print to the command, as well as a save and rename function. So here we have the clean raw data. Again, largely it's just applying the collision apply method for normalization, the load data method. After that, we run into the computation section, which we have the high collision areas, the high fatality areas, and basically this is where all of our aggregations are done. Injuries per month. Like I said, there's about 16 of them. You have the section that saves the data, whether it's a data set or a data frame. We do a file name change so that things are more predictable and they can be used easier. And then I created a wrapper method to do the save and file name change to help reduce on the clutter. And then lastly, we have all of our print statements for each one. Some of the ones that were the same were able to be done in a print wrapper to help reduce with the code. We'll run this. So you can see right now there is no outputs folder. All of these will get put to an output folder So it will get created as the program runs. So I've already done the SPT compile and assembly, and I've moved the jar file over to help save some time. So now we will start up Docker with 5 workers. And then we will bin bash and run the code. This will take some time to run, so likely I'll skip forward. So you can see now that it's run, it has correctly aggregated and printed out for our print statements. So a couple of cases, there's a lot in here, so it's a lot of data to process. But you can see it's printing out correctly to the command window. Also, now we have an inputs folder, which we can see it's written the clean data. We can check a few of these. So high collision area, which is the main goal of the project. You can see we've printed out the information we needed. Some of the shorter ones are done by year ones as well. For any of the ones per town, you can see it does in fact calculate, in this case, fatalities by all of the towns in the state of Connecticut. So the visualization part, again, was done in Excel. So here, the main goal, we used high collision areas and high fatality areas. So you can see Waterbury Main Street in the lead for collisions, as well as fatalities on Main Street in Waterbury. So don't drive on Main Street in Waterbury. Some of the statistical data, did collisions per year. You can see 2023, about 65,000 collisions. The support also broke down by collisions per month. Fatalities by year as well broke down fatalities per month for better statistical data. Here we show fatalities per year per city. So here's just 4 examples. Again, looking back at that CSV file, it does calculate every city, but that's a bit much to put on here. So you can see Waterbury 2023 as of November, because December data wasn't in, they were at 8 fatalities. Injuries per collision by year. So this aggregation takes the total collisions and compares it to how many injuries resulted from those collisions. So example 2023, about 65,000 collisions resulted in about 21,000 injuries. Broken down a little bit further by year and month, we can see the same data just distributed monthly. So here we have injuries per year for given cities. Bridgeport, for example, 2023 had 1,427 injuries. Collision event types was one of the aggregations. You can see it looks like motor vehicle in operation is the highest, which makes sense. Parked motor vehicle, guardrail face, and it goes all the way down to some of the lower collisions. So 1 fire explosion in 2022 and 2 railway vehicles in 2023. Manner of collision. This is your rear end angle side swipes. All years seem to point to getting rear-ended is the highest. Contributing factors. So we have none, weather conditions, unknown, animal, glare, other, and visual obstructions, sorted by year. Collision lighting conditions. So we have daylight, dark lighted, dark not lighted, dusk, unknown, dawn, other, and dark unknown. also sorted by year. Here we have weather conditions by year. So you can see clear, and almost every year has more accidents than you do in rain, cloud, or snow. Road surface conditions, dry seems to beat out all of the other road surface conditions every year as well, which is a bit surprising. And the moral of the story, don't drive in Waterbury on Main Street in December in the daylight on a clear, dry day. And if you do, watch the car behind you. You're about to get rear-ended.